Okay, well, thank you very much for this kind introduction. Let me thank the organizers for organizing this very nice event. Very glad to be here. As you have understood, I'm a physicist. Nobody's perfect, but I know I'm not the only one in this room. Anyway, I will try to entertain you with this problem, which I found quite interesting. As you will see, there won't be, strictly speaking, any reflected Brownian motion or random walks there, but you will surely recognize some familiar tools. And that's why I hope that's why I thought that you could probably appreciate it. So this is a work that we have done relatively recently with my two colleagues, Anupam Kundu from ICTS Tata Institute in Bangalore, in India, and for my colleague and friend Satya Majumdar, who is from Université Paris-Saclay. And these are, I mean, most of the things that I will talk about is contained in these two things. Well, this one you can have access to. This one is not yet there, but it will be soon. So let me start with a kind of brief outline of what I want to tell you. I will start with some kind of motivations and a little bit of background and why we are interested in these questions of studying the minima of random walks. Then I will describe our main results, and I'm sure I will have time to sketch some ideas of the derivation of these results. So let's move on. The question actually, well, say I got interested in this problem from my works on disordered systems, and in this context, what you are typically facing too is studying some complex landscapes, which might be some energy landscapes. So typically, this is this picture, which I stole from my colleague Valentina Rose from Orsay. So you have typically some cost function, which is, okay, for us physicists, usually is a kind of energy. And it's a function of the configuration of your system. And a typical picture that people have in this context is this quite rugged landscape in the set of configurations. Now, of course, usually this is a very high-dimensional landscape. And the question that you may be interested in is what can be said about the number of stationary points. And the typical, I would say, the reason why we ask or why we are interested in such a question is that basically we have this energy landscape, and we have to think, if you think of the dynamics of your system, well, that will be a kind of jump process between the different minima of this complex energy landscape. And as you may expect, in particular, if you are at low enough temperature, your system may be trapped in this local minima. And in a sense, the number of minima might be related to the entropy of your system at very low temperature. Okay, so that's a very natural question in this context. And in fact, this has been studied, or this has been raised at least in many different areas. The first one is the one that I mentioned, which is in the context of energy landscapes. This has been pushed forward, indeed, mainly by people who have been working on disordered systems, and probably the emblematic model that you might have about is the spin glass systems. And there have been many names attached to that. This is a quite rapidly this has been a quite rapidly evolving field during the last 10 years or so, both in math, I mean, with in particular Gérard Benarous, and in physics, with also quite a few names there. Now, there are other contexts where these questions are quite natural. Another one is string theory. I will not enter too much into the details, but typically many string theories have arrived to a point where they have a kind of complex landscapes, and in that case, the various minima essentially correspond to the possible vacua of the world we are living in. And it turns out that there is a huge number of such possible vacua in these string theory contexts. And it's a quite important question, in particular, that has been raised by Susskind, who is quite famous in this field. Yet another one is in the context of fitness landscapes and in evolutionary biology, and there are many models. One of them is this famous House of Cards models, which have been studied by lots of people, Fisher and White, of course, but more recently, both in the math and physics, Beresticki, for instance, or Joachim Krug. So you see that these are quite natural questions in many different areas. Now, it turns out that for most of this problem, these are, I mean, these landscapes are really constructed, or they live, if you want, in a quite high-dimensional space. But what I want to show you is that such questions are also relevant in lower dimensions, and in particular in the simplest case of a one-dimensional landscape. Okay, so that's what I want to study here. Okay, so the model that I want to discuss here is very simple. Is just a one-dimensional random walk, and I want to see this trajectory of a random walk as a random energy landscape. Okay. So the model that I will look at is this one, and I will be mostly interested in the case where the jump distribution phi of eta is continuous and symmetric, and a question that I will address in particular is basically what can be said about the number of minima, the number of maxima of such random walk. So here in the red points, I have just marked the minima. Just by convention, I will never count this first guy as a minimum, and the last guy will also never be no minimum or maximum. I just exclude them. You can add them if you wish, but just for sake of clarity, that's the choice I will do here. And in particular, a natural question that you may ask is how does it depend on this phi of eta? Okay. So I will actually consider a quite wide range of such distributions, either regular random walk. By this I mean phi of eta, which have all of these moments which are well defined. But I will also consider the case where phi of eta may have heavy tails. Okay, and that's what in physics we usually call Lévy flights. I'm not sure this is a very well chosen word, but this is what we will usually call it. Okay, so this phi of eta again actually covers a very wide range of such random walks. So there are actually some clear motivation as to why we want to study such a 1D landscape. First one actually comes from a famous model of disordered system, which is called the Sinai diffusion model, which you have probably heard about. So Sinai diffusion is simply the diffusion of a particle on a line, but it moves in a landscape which is generated by a Brownian motion. Okay, so that's the original Sinai model, which is usually defined both in continuous space and time. So the model that I have in mind, if you want, is a kind of discrete version of the Sinai model, where you have your particle that basically jumps from one side to another, and basically this is the energy potential that my particle feels. Okay, so again, as I said, for such a model, well, it's clear that if you have a large number of minima, well, again, as I said, your particle may get trapped in one of these minima, and it may take a long time to eventually cross these barriers and going from one minimum to another. And counting the number of minima again will give you an estimate or some characterization of the slowliness of the dynamics. Now there is actually another nice connection between such a random walk profile and a statistical physics model, which is the one of fluctuating interfaces, which you probably have heard about, which is quite simple to expose in the case where this phi of eta has just this Gaussian distribution. Okay, so imagine that I have such a random walk like that, and these etas here are just simply Gaussians. Now, if you just want to look at the probability weight of such a contribution, well, that will be simply this product of Gaussians, because these etas here are just independent. And you will, if you want to write, if you want the, the distribution of your path, well, that's what you will get. Sorry? Yes? On this one? Yes, I see. Okay. Hide video panel, I guess. Floating meeting controls. Yes. Okay, good. Sorry. Okay, so now if what I was saying is that if you come back to this problem, well, basically, if you write the joint distribution of these positions, well, this is simply this product of exponentials, but this product of exponentials is the exponential of the sum. And you see that what you get is basically the Gibbs measure of an elastic interface. Okay, so essentially, you can think of this simple model where I have my xi, so you have beads at some position x, and essentially, they are just connected by elastic springs. Okay, so you would have here your, say, x1. You will start from x0, x2, etc. Okay, so that's a natural model for an elastic interface, and that connection between Brownian motion and elastic line, or random walk and discrete elastic interface, which is usually called solid-on-solid model in the StatMech statistical physics community, has been widely exploited. Now, it turns out that people have been interested in the context of the minima of this. So if you think of it as a profile of some elastic interface, well, you can see that, that the number of minima in some sense characterizes the roughness of the interface, right? If I have a lot of minima, then clearly that's the signature that my interface is quite rough. On the other hand, if the number of minima is very small, well, you will expect something which is, on the other hand, much more, say, less rough, much smooth. So in this case, you see there is no a priori knowledge of the landscape, in the sense that, I mean, for this precise model, right? Because what you get in this case is just that. So this is just the probability weight of your interface. So I forgot here the idea of a landscape. There is no landscape now. This is just, I want to see that as the Gibbs measure of a given realization of my interface. Okay, so in that case, this is, I don't want to, I mean, in this context at least, this is not anymore an energy landscape, sorry, but it's just really the trajectory of a given polymer, if you want, or a given interface. Okay. So there again, the natural question is, if I want to look at the roughness or characterize the roughness, what can be said about this number of minima? And actually, there was this study actually started with this paper in 2000 in the group of Rosia, Virginia Tech, and this paper actually had generated lots of offsprings, but eventually it turns out that people were only able to do computation of the average number of minima, but actually nothing really were done on the fluctuations. In fact, this observation is actually quite general if I think about the other models that I've been discussing, even in this complex energy landscape that I've been discussing in high dimensions, like the works of Benarous and co-authors. Basically, what they are able to do in all these problems is computing the average number of stationary points. And that usually starts with the Katz-Rice formula for the Hessian matrix. And then this Hessian matrix, typically in this complex energy landscape, are random matrices. And what you have to study is basically some determinants of high-dimensional random matrices. Okay, but that's usually focused on the average number. And what we wanted to have is a model where we can do more and eventually compute the full statistics. Okay, so that's eventually what we did. In this work that I want to talk about. Now, I want to say that if I think of this random walk problem, but if I look at the simpler one, which is the lattice path or Bernoulli random walk, so imagine that you just have a plus minus random walk. As you probably know, these are very classical questions, and in fact, many people have contributed to this field, since these are very natural combinatorial objects. I just mentioned here the names of Narayana, Cratton-Taylor, or Stanley, where people have studied this in great detail, but again, mostly restricted to this kind of Bernoulli random walk and using quite combinatorial approaches. And in that context, this is just terminology. The terminology differs a little bit. Usually, terms. I mean, if you look at the nice review by Cratton-Taylor, the stationary parts are what he called terms, and the local maxima is what usually in this context people call peaks. Okay, so that's just, but that's exactly the same kind of things. Now it turns out that we got interested in a more recent problem or more recent papers by Jean-Maxime Labarbe and Jean-François Marqueur, who consider this the case of constrained lattice paths. Okay, so they have this nice paper where they look at these Bernoulli random walks first, but also bridges, excursion, meanders, and trying to compute the number of peaks for such specific Bernoulli random walks, and again using mostly combinatorial approach. Yes. Yeah, sure. Yeah, I will come to that. Yeah, of course. Yeah. At least for the simple random walk. Yes, of course. Yeah. I will come to that. Indeed. Anyway, what they looked at and what they obtained is first results using combinatorics for finite number of steps, and then they were able to understand the large n limit for which they derived typically a central limit theorem. So if I denote the number of minima, so if you just look at the standard Bernoulli random walk, well, it's quite easy to see that the average number would be just 1/4 times n, right? Because you have essentially 4 different types of situations, which are basically either this one, either that guy, or either this one. And if I count the number of minima, well, only this guy will typically count. Okay, so that's just 1/4 of these edges, if you want, that will count. Of course, the result for the variance is less trivial, and it turns out to be this n divided by 16. So what we wanted to do is basically try to extend this result for constrained random walks, but with continuous jump and increment distribution. Okay, so indeed the extension for the standard random walk is just trivial for some reason, as it was pointed out. But clearly, if you go to constrained random walks, of course, the situation is pretty much different. And that's basically what we did. So let me just describe the results that we got. So I will here present the results for 2 different situations. The first one is the case of the free random walk, which is to some extent quite similar to the one studied before. And the one that I want to discuss for you in more detail is the case of the meander. Okay, so I want to ask this question now for a random walk, which is conditioned to stay positive up to step n, and I want to count the number of minima. Okay, and as a byproduct, in particular for this random walk meander, I can actually look at different types of observable. But for instance, you can ask what's the number of minima up to the first passage time. This actually, with a bit of work, you can get from this random walk meander. So let me just give you the result that we get. The first one is that, okay, if you just look at the free random walk, what you find is that these probabilities given by, so first the number of minima cannot be larger than n by 2 for some steric constraint reasons. And then it's given by this binomial coefficient, which actually can have relatively simple combinatorial interpretation in terms of composition. So I will not enter too much in the details of that. It's not totally trivial, but it's easily doable. That's how these people derive this result. The observation that you can do is obviously that this result is obviously universal. Okay, it's pretty clear that if you want to count the number of minima for such a random walk, well, what you only need to know is the sequence of signs of the jumps, okay, the plus minus, but you don't need to know explicitly the size of these guys. Okay, and therefore, indeed, this result is obviously universal. Universal means independent of the jump distribution. Now, what about the more complicated case and more interesting case of the meander? So in this case, the quantity that I want to study is now a joint distribution. So it's not normalized itself. I mean, it's a joint distribution, which is, I want to compute the probability that the number of minima is exactly m, and that this jump, that the random walks stay positive up to step n. Okay, so if I take the marginal over m, I will get the probability that this random walks stay positive up to step n, which is the survival probability. Okay, now clearly here you see that the dependence on phi of eta is much less trivial. Okay, because it's clear that now in this context, the size of the jumps, may play a role. Now it turns out that this result turns out to be completely universal, and given by this more complicated formula, which is given here. And again, I will try to show you how one can derive this result. Again, as I said, this is universal, completely independent of the jump distribution. So in a sense, this can be viewed as a kind of generalization of Sparr-Anderson theorem. In fact, we also use, in the part of the proof, we have also to use this Sparr-Anderson theorem. But you see that that's really the reason for universality in this case is really due to the universality of the Sparr-Anderson theorem, which is much less trivial. Yeah.
Are you assuming that the increments are symmetrically distributed?
Oh yes, they are symmetric and continuous. Yes, but actually, okay, we could extend it. We could easily. The method that I will present could be easily extended to the asymmetric case. We have not done it, but this requires some work, but this can be done. So maybe I guess many of you know the Sparr-Anderson theorem, but I thought maybe it's just useful to record what the Sparr-Anderson theorem is. So if I look at such a random walk here, which is which starts from 0, and which have these increments which are continuous and symmetric. And if you look at this probability, which is the probability that all these guys, x1, x2, so not the red ones, but the true random walk are positive up to step n, which is what we usually call survival probability or persistence probability. This is given by this very nice formula, and it's completely distribution free. Okay, it's totally universal, and there is actually a simple proof of that, which I can maybe try to sketch. But maybe something which is useful to write first is that the generating function of this Qn is actually very simple. You may probably recognize it, but the generating function of this Qn. So if I compute the, so if I write this guy here, sorry, well, this is just the series expansion of this guy. So it's very simple. So let's try to prove that in 2 lines. Okay, that's a proof that I like. I had not seen it elsewhere. Maybe you do. But it starts with this picture, which was actually already drawn on the blackboard when I arrived this morning. Probably Vlad has written it. I don't know. But so I look at this random walk here, and I want to look at the distribution of the time of the minimum. Okay, so I just want to look at that, and I just consider the time of the minimum, and I want to say something about the distribution of this guy. Okay, so what's the probability that the minimum T min is equal to m? Okay, so that's what I'm after. Well, as it was briefly sketched in one of the discussion, I think yesterday, there is a nice way to compute this distribution, which amounts to separate your trajectory in 2 halves here. And what you observe is that, well, first, these two parts are independent. This is a well-known fact for random walks. But on top of that, if you look at what's the probability of this bit here and the probability of that other bit there, well, if you just shift the origin, in this case, well, you see that the probability of this guy is just to stay above this line. So that's starting from 0 and remaining positive up to step n minus m. So that's a survival probability, exactly the one that I was after. And on the other side, that's exactly the same. Okay, so obviously, this probability distribution is just this product. Fine. Now, at this moment, I don't know what this Q here, but what I know is that this distribution has to be normalized. So let's write the normalization condition. And the normalization condition is simply that, no? Is that this, oops, shit. Yeah, that's, should cancel this, I guess. Okay. So this guy has to be normalized. Okay, so that's what it reads. Now, you see this has a nice convolution structure, so I would like to take the generating function on both sides, which is very easy to do. This will give me on the one, so if I do that, that will give me the q tilde z squared, right? And on the other hand, this is just the generating function of 1. So you very easily get that result here. Okay, so that's a very simple proof of the of this Spahr-Andersen theorem. Good. So let's come back to the to our results. So I want to maybe say what we can get also for the maxima of up to the first passage time. So again, here we can compute this joint probability, which is the probability basically that the number of minima is exactly m, and that the first passage time arises between step n and step n minus 1 and step n. Okay, that's again something that you can get from the meander. It's not totally trivial, but okay, this can be worked out, and the result is there. Again, of course, it's universal because the other one is universal. Now there is something else that that can be derived, which I want to discuss briefly, is that now I can just sum over n. So I just want to look at what we usually call the number of minima up to the first passage time, but no matter this first passage time is. Okay, so I just sum, I take I just make the sum over n of what I have here, and what we get is a fairly simple expression, which is given here. And I hope I will have time to give you an easy way to understand where this comes from. Now, you can even look at the large M behavior of that. It's quite easy. Okay, we'll not discuss too much there. But if you look at the large M behavior, well, this goes like 1 over m to the power 3 by 2. Well, this is relatively expected because for a random walk, basically the distribution of the first passage time has a 1 over n to the power 3 by 2 decay. This is just Spahr-Andersen. And the typical number of minima is roughly proportional to n. We have seen it's n by 4. And that now naturally gives you this 1 over m to the power 3 by 2. Okay, that's very simple argument. Now, to get this 1 over 4 root pi, of course, you need to work a little bit more, and that's what we did. Okay, so that's for the result. Let me just, because I've shown formulas, it's always nice to see how this formula look like. So that's typically what you get here for the distribution of the number of minima for a random walk for n, I think, which is 100 here. So these are results of simulations for different jump distribution. You see it columns very well. You see it's typically, it has a typical Gaussian shape centered at 1/4, which we expect. Now, on the other hand, if you look at the first passage, so the number of minima up to the first passage, well, it has a completely different shape. So it goes, say, from Gaussian here to something which is this kind of power law. So this is log scale with this 1 over m to the power 3 by 2. But again, you see that if you do simulations, you really see that all of these data fall on the same curve nicely. Okay, so let me just try to give you, I will probably not have time to go to that, but in the special case of the the free random walk, we actually can go much further. Of course, I mean, for a random walk, if you look at the number of, for a free random walk, the number of minima or maxima is just the same. But you would like to know something about the joint distribution of these two guys, okay? And this is something you can easily do. You will see, I will present a method which allows to do that quite easily. And you can get any kinds of other quantities you would like for this walk. This one is relatively simple. You can compute correlation functions, and as you would guess, the number of minima and maxima is quite strongly correlated. I mean, the variance goes, the correlation function goes like n. Anyway, the case of free random walk can actually be handled in a very easy way using a method that I can show right now, and you can compute all kinds of generating function you want. And that's what I want to discuss in the remaining time. Is it clear, I mean, about the results that we have? Okay, good. So I will start with a very simple approach. I will not use essentially any combinatorial techniques here. First, because I'm not I'm not a specialist of this. And second, because when you have to deal with a continuous germ distribution, it's not so easy to really to do this kind of combinatorial approaches, which is much more, well adapted to the case of plus minus or discrete jumps. So I will devise some analytical approach if you want. And the first one is a recursion approach. So we want to, I want to solve this problem in a recursive way. So I will focus on the free random walk just to illustrate the ideas, but I will tell you how this can be extended to the more complicated case of constrained random walks. So to write recursion relations, actually what I want to essentially write are some kind of backward equation. So I want to understand what happened during the first step. And for that purpose, I will introduce this joint probability, if you want, which is which I call Q plus minus of Mn, which is the probability that the number of minima is exactly M, and the first jump is positive or negative. So in this case, it's plus, but you have the Q minus, which is just the analogous. Now, it's quite easy to write a recursion relation for these objects by simply trying to understand what happens during the first step. Okay, so these are the equations that you get, and they are very easy to understand, right? So let me just write this very simple thing here. So imagine that I start with a plus. So this is the first equation, which I called 1. Okay, so you are going up. So that's the first guy. And then at this stage, essentially, you may do two things may happen. Either you continue with the up, that will happen with the probability half, or you continue with the down. And you just, this will also happen with the probability half. But you see that in doing so, you have not created any new minimum. And therefore, the number of minima that you will have on that part of the random walk has still to be M. Okay, so that's basically these two guys. Okay, so either I start again with a plus, this happens with the probability half, and I need to have M minima, but this time for a random walk of step n minus 1, and the same here. Now, if you do this minus step, so that's the second case, if you want. Well, I guess you have understood. I mean that you do that. So with two, either you go down or you go up. Now, if you go down, there is no minima created, so you will need again to have M minima. So that's this guy. On the other hand, if you have done this plus here, which happened also with probability half, well, in this case, you have created indeed a minimum, and therefore, on that side, you only need to have M minus 1. So it's very simple. And obviously, you already see that at this stage, this is completely independent of the jump distribution. There is the phi of eta doesn't appear for obvious reason. And you need also to start for somewhere. well, this, you can convince yourself that this is only true for n greater or equals than 3, and you can just work out the case n equals 2 by hand, and that's the starting point of your, this is very trivial, that's the starting point of your recursion relations. Now, they are simple enough that you can solve it using nice generating function techniques, and you can get everything you want. Okay, so that's basically the way you can do that. Now, the problem is that this works very nicely for the free random walk, but as soon as you start to have some boundaries, or if you start to have some constraints on your Q's, so for instance, if you now insist on having them always positive, the situation becomes much more difficult. You can still write such equations, but unfortunately, they are much more complicated to solve, and in general, you don't know how to solve them, except in some very special cases. I mean, people who, you know, for instance, the Laplace random walk is quite nice. It has some very nice properties. You can transform these integral equations in differential equations and solve them in a very nice way. But otherwise, except for these very special cases or generalizations of it, you are just stuck. Okay, so you would like to have something like that. Okay, so that's what we want to do. Now, the method that we propose to use is to describe an auxiliary random walk, which is a random walk that you construct from the local minima of your random walk. Okay, so this is one realization of it. And so it's not exactly the converged Smyderant. I mean, it has some similarities with it, but it's really the random walk constructed from these minima. Okay, so that's the nice object to look at. Then obviously the number of steps of this random walk is not fixed, but as you will see, this is not so bad. And the first question that we want to ask is, can we say something about the transition probability, say going from y1 to y2 in say n steps of the original random walk? Okay, so that's something that one can compute relatively easily. I will have maybe 2-3 bit technical slides, but the computations are quite simple. So I want to compute the transition probability, say from y1 to y2. So I mean, since these two guys, since in between, say I cannot have any minimum, well, the trajectories typically look like that. So I have up steps followed by down steps, and let me just denote the probability of this path here, transition probability on that side, the probability jump probability on that other side. Since I will consider symmetric, these p plus and p minus are just the same. But again, this could be done in a more general way. What we know in particular is that the Laplace transform of this distribution, well, is just a simple random walk. But these random walks are constrained to have all the steps being positive. Okay. So that's what we have. And on top of that, in particular, if you just set s equal to 0, so if you really integrate, so if you look at that, and if you integrate over y here, well, basically, I mean, the probability for such trajectory is obviously 1/2 to the k, and there's nothing really deep there. Now, this being said, you can easily write an equation for this quantity, which is psi. Okay, so this is just what do I need? I mean, I just do this path decomposition. I first need to have these up steps followed by down steps, and then I need to sum over the values of the peak of the maximum, and I will need also to sum over the position of this peak. Okay, so that's my that's the expression for psi y2 y1. I just want to draw your attention here on the fact that k starts from 1, because I really insist on having 2 minima here. So essentially I cannot have a simply decreasing step here, or a simple increasing one. So therefore, I really need to have at least k starting from 1. This observation will become a bit more important in a minute. Anyway, if you just massage it a little bit, I mean, it's quite easy. I mean, first to show that psi is continuous, I will need that. And it's also symmetric. If you just rewrite this by making a shift of y by this max, it's easy to show that it's actually a function of y1 minus y2, and it's actually symmetric. So it's only a function of the absolute value of it. Okay, so I want to have more on that. And what I would need is basically the generating function of this guy. So it has a very nice convolution structure. So I can, again, write the generating function of this psi in terms of the generating function of this guy. Okay, so this is the J. And so I have this expression here. It's not fully explicit, and it depends at least explicitly on the germ distribution phi. But it turns out that in the following, in a minute, what I will need is actually not really this psi tilde, but its integrated version over Z. So that means that if I look at this guy, what I really need, we will see why. I would like to have the value of this guy, but integrated over the final point. Okay. I mean, you understand why I guess I do that. But first, it's easy to get the integral of this generating function here, because we have seen that this pk integrated over x is just half to the power k. So I just have this geometric series starting at 1. Nice. So now how can I relate the both? Well, I mean, there is a very nice identity here that if you do the integral of that over u, well, it's symmetric. So you can just have twice the integral over from 0 to plus infinity. So it has this structure. But now you see that this guy here, or say this guy, is just the derivative of this guy with respect to v. And therefore, you can integrate it explicitly. And it's totally independent of your germ distribution. OK? So that gives you this nice factor, z over 2 minus z to the power squared. Well, there is a very simple interpretation of this guy, of this result. So I have this quantity, but now I can, okay, it's very simple, right? So I can just invert this to compute psi of y1, y2, n, and it has this very simple expression. The reason why it's so, I mean, obviously, I mean, I didn't need somehow to do all this computation, but you see this 1 over 2 to the n, I can just decompose is 1 over 2 to the k. This is the probability of that bit, the probability of that other bit. And then I need to have this the position basically of my maximum, which can be nu. Okay, so that's actually not so surprising result, although I got it in a very different way. Anyway, now I'm in a good position to compute this probability. Okay, so how does it work? Well, it works as follows: that oops, sorry. So now I'm in a good shape in the sense that I can somehow compute the probability weight of a trajectories by focusing on this effective auxiliary random walk, which is built from the minima. So basically, the probability weight, you see, I mean, now all these bits here, I know the transition probability. They are given by this psi function. Oh, yes, please.
Not independent, or almost independent, right?
Yes.
Because if you know that it's a minimum,
yeah,
you know something about the future. So
well, yeah, I mean, in fact, what you can show is that the only correlation is that they have to sum up to capital N eventually.
I'm just saying that they are not mutually.
These guys, they are actually.
The increments are not independent, because if you know that at y1 you have a minimum, then you know something about the future. You know something about the next step, right?
Well, in fact, what turns out is that the only correlation that you have between all these guys is that there is a global constraint that these ni's are actually just they need to sum to n. But on each segment here, they are totally independent, right? Yeah, exactly. Yeah. No. Yeah. So that actually is encoded in the in the weight that I had here, right? I had always a up and followed by a down, and that takes. The first. No. It's okay. Yeah. Well, we can discuss, but yeah. But there is one observation still, indeed, is that these two bits here are different, right? The first bit and the last bit are indeed different. And okay, I will just call them, say, sorry. So I will just call them psi bar. Yeah, so that's what I call psi bar. Okay, so these guys actually are indeed different. Okay, but still independent of the rest. But they need to be, they can actually be different in the sense that, for instance, you see, I can only have up here. While in all these cases, I necessarily have an up followed by a down, up followed by a down. In this case, this is not necessarily the case. So I can only have up trajectories. And so therefore, there is a slightly different contribution. And I can just redo essentially the same kind of observation computation that I did before. But now, compared to what I had before, I need to start from k equals 1 instead of starting from k equal to 0. Anyway, that adds a term to this generating function, which is basically this guy. Okay, so that's what I had for the other piece. But that guy actually has an additional constraint. And if you just sum them all, that's what you get. Now, with that, I am actually essentially, I can actually compute what I want, because the distribution that I am after is just obtained by summing all this probability weight and integrating over all the possible positions of the y's and summing over all the possible configurations of the ni's with the constraint indeed that they need to sum up to n. So there is a constraint sum, which is, I just wrote it a bit in a bit sloppy way here. But the nice thing anyway is that what you want to do is eventually take the generating function of this guy with respect to n. Okay, so everything will then decouple. And when you do that, well, the result is extremely simple, is that when you do this integrate, so this generating function, what you get is the product of all the generating function of all the bits, right, as expected. All the guys in black here with the psi's, they will produce this z to the power 2 minus z squared to the power m minus 1. They have m minus 1 blocks. And there are 2 blocks missing, which are the first guys, which contributes to that bit, and the last guy, which contributes to that guy. Anyway, you see that the expression at the end of the day is quite simple. You get eventually that, and it's quite easy to obtain the result that I announced before. Okay, so that's a very nice way to do this computation. Of course, as I said, for the free random walk, there are other ways to proceed, which are much simpler. But it turns out that it can be this auxiliary random walk from the minima is actually, okay, I will not comment too much on that, that it can be easily done for the, or can be easily, it can be extended. It's not so easy, unfortunately, but it can be actually done for the meanders. I will not provide all the details. But okay, if you just naively, if you would just to say, well, that these two events are independent, well, you would get that this is just the probability of having exactly a minimum times the probability of the survival probability, if you want. And this is just given by the Spar-Andersen theorem. So that gives you the flavor that this result might be universal, but as you can expect, this argument is completely wrong. In the sense that these two events are obviously not independent at all, and you need to work more. So this is what you can do with this auxiliary random walk framework. Again, it's a bit cumbersome, a bit technical, so I will not present it here. I just want to maybe show you the kind of result that we get is that eventually, it's actually convenient to separate two types of trajectories, the one that ends up with the up steps, the one that ends up with the down steps. That will give two different contribution. But what you see that appears is that there is this quantity Qm, or here Qm plus 1, which is the survival probability for this effective random walk. Okay, so that's actually really at the heart of the proof here. And I just want maybe to show you, I cannot really show you all the details of this computation, but I can show you a simpler situation where we clearly see why this Qm comes out. And the simpler example is the number of minima up to the first passage time, because that one turns out to be quite simple. So I want to look at the probability that there is exactly m minimum up to the first passage time. So it turns out that it's useful to look at the cumulative distribution, which is the probability of observing at least m minima up to the first passage time. Okay, and this actually can this question can be reformulated in a simple way in terms of the auxiliary random walk discussed before. Okay, so let me just draw this simple cartoon. So let's look at a random walk which have achieved at least m minima up, at least m minima. Okay, so I don't know exactly what happens after that, but what I know is that it is the probability for that is basically the probability that this random walk here stayed above 0, because if the minima stay above 0, that's sufficient condition, necessary and sufficient condition for the whole random walk to stay positive. And on top of that, I need to have this last step here, which needs to be up. So you see that I can now just say that this cumulative distribution is just the survival probability for this effective random walk. Now, this effective random walk is characterized by a continuous and symmetric jump distribution, which I've discussed before. And so I can easily apply Spar-Anderson theorem to it. That gives me this QM. And on top of that, this guy must be up, okay, because this one has to be a minimum. So I need to take care of that. So that adds this factor half here. But the expression is then very simple. And if I want to look at the distribution itself, I just need to take the discrete derivative of these guys, and I obtain this nice formula that I showed. So you see that almost without any computation in this case, just by analyzing this effective auxiliary random walk, you get this nice result. Unfortunately, I don't have any simpler argument for the meander, but at least I have a formula and I know how to compute it. Okay, so let me just flash very rapidly some conclusion. I showed you that we can get this the full statistics of the number of minima for constrained random walks. Again, for unconstrained ones, life is much simpler. But I showed you that for constrained, in particular for meanders, but we can also do other ones. It's kind of extension of the Spar-Anderson theorem, right? Spar-Anderson gives you what's the probability that you stay positive up to step n. This is a universal quantity if you start at 0. Now, there is something even more universal, and which is the probability that you stay positive, and that on top of that, you have m minima. This is also totally distribution free. Okay, so let me just flash some maybe some questions. Of course, we know how to do the random walk problem. That would be nice to have some other type of process like integrated Brownian motion or integral of random walks. That's something that would be quite nice. Another question that I may suggest, in particular to specialists in the audience, is whether there are some nice natural extensions of these questions in higher dimensions. I'm sure that there are. In particular, we know that there are some very nice extensions of Spar-Anderson by Zakhar Kablushko, Vlad Vizovsky, and Dima Zaporodets in these various sets of very nice papers where they did extend this Spar-Anderson theorem to higher D. I mean, whether this can be extended there and whether that would be also distribution free. This I leave you for future works. Okay, thank you for your attention.
Thank you very much. We have 5 minutes for the questions.
Well, there's some combinatorial literature on peaks and valleys of random permutations.
Okay.
So I just wonder if your model for some parameters would, in the limit, go to a random permutation.
Yeah, that's a good point. I'm not sure, but I have to think about it. Yeah, I don't know so well this literature. Yeah, that's certainly, yeah, that would be nice to have for sure a combinatorial interpretation of this formula, which we have not found. And yeah, that could be some reformulation in terms of permutation. Yeah, that's a good suggestion. I haven't thought about it.
Thanks for a really, really nice talk. So I'm just had in my mind the at the beginning the energy landscape. So this could be a dumb question. So how hard would it be to think about the number of minima less than a certain y and greater than a certain y?
Yeah.
Like how is it just stupid to ask such a question, or?
Yeah,
just
I mean
incredibly
that's
difficult?
no, that makes sense, of course. That makes sense. I mean, of course, counting the minima is okay, is already a nice information, but of course you would like also to know really, I mean, the size somehow, the size of this valley, right? I mean, because it's not because you simply have a minimum that you will get stuck forever, right? So you would like to have some information on the size of this. Yeah, that's so there are actually some approaches that have been developed for the context of the Sinai model using this real space renormalization group by Ledoussal, Fisher and company, where they can have. Also, I know that these are relevant, questions that have been studied also in the math literature. Yeah, I think that, so we are thinking a bit about along these lines. I think that for the one homeworks, using, I think this, this path decomposition is probably hard to do, but this recursion relation is probably amenable to more computations in that direction. Yeah.
Thanks. So just to continue from this last question, would for example, if you looked at contact points with a convex minor and the trajectory, would that be something that captures this feature that you have more extensive local minima?
Right. Yeah, that's I don't know. Maybe there are already results for that. I don't know that. You know the literature on this better than I do. Yeah. Okay. I mean that's a bit harder problem. But I don't know. Okay.
I don't know the physical interpretation, right?
How, sure. Yeah. No, that's a natural question. I agree. Yeah. Sure. Okay. Yeah.
Yeah. So on sort of the physical intuition, what you look as the number of minima among the nearest neighbors. So I thought it could be more physical to look into, let's say, a longer neighborhood, like 2 neighborhood or maybe R neighborhood. It's not doable, but
yeah. Okay. Yes. But it's more complicated. Yeah. Okay. Yeah, that's true. I agree.
So I have a question before then I'll give, which is you talked about the higher dimension.
Oh yeah.
And so I'm guessing that somebody's done simulations. Has there been, is there a suggestion for universality there in
I don't know. No, we haven't done anything. I mean, it's really a true, yeah, first, what would be what would be really the question to look the observable, right? Because they have a generalization of Spar-Andersen, which is already not totally obvious. And how to generalize this notion of minima. Well, there are several of them. Maybe the points which are nearest from the center, for instance. So I don't know, but this has to be no. I don't. It's really not a completely open question. Yes, it's not that I have already the answer. But I'm sure there should be some universality there.
So in Spar-Andersen, you have one variable, you have a
yes.
time n. You have shown one example with 2 variables. And is it believed that you could go further and have a universality with more variables? And how far?
Yeah, well, so that's actually, okay, this was a bit one of the motivation that we are pursuing for some years now, is trying to find universal quantities. I don't know. To be honest, I was not convinced at all that these guys should be universal at first. Yeah, I don't know. That's if you have any suggestion. Yeah, no, I don't. Yeah, that's something that we are thinking of. Yes, sure.
And small question: is it possible to generalize to autoregressive processes?
I don't know. Yeah, that's well, okay. I think that. I think that one case that could probably be doable is the. So of course, I think the recursion relation approach. Okay, one has to modify it a little bit, but probably it could be extended to that case, and at least maybe we could hope that for some cases, jump distribution exponential case could be maybe doable. Yeah, that's. I think that's one case, maybe one further extension that could be maybe done. Yeah.
Well, going back to the energy landscape you started
Right.
from, there are many results for minima of Gaussian random fields.
True.
In particular, the number of minima
Yes.
of Gaussian random fields in the continuous case. So it can be multi-parameter in that case. So in France, there is Anne Estrade. Maybe you know her.
Who, sorry?
Anne Estrade in France.
Okay, no, I don't know.
And then there are other results on the distribution of the heights of the minima of Gaussian random fields.
Okay, yeah, I would be happy to know results. I mean, some references on that.
Okay. There are no further questions. We had many. Let's thank
Okay, thank
Gregory
you.
again and